Okay, let's get started. Where's my slides? Oops, it's too big. Okay, let's get started. Hello, everyone. Thank you for joining this session. So my name is Zemin Zhao. This is a graduate level class, system security, attack and defense for batteries. For graduate students who are taking this class, I hope you can just turn on your camera if there is no serious privacy issues. So we can have some close to in-person interaction experience. I can see your face. I can get a feeling if you are following there. For other students, like undergraduates, you are just treating this like an open seminar. You don't have to do this. Okay, so I want to let you know that first of all, I'm recording this class on the UB Cloud and also to YouTube. So if you have any problems with that, if you don't want to show your face, because accidentally I may post your face on internet, and please let me know. And I hope you have a pen and a piece of paper in front of you, or like a notebook for taking notes and also drawing things, because to understand how things work, we probably need to draw a lot of things, especially for one of the practice I think is very important is draw the stack, especially for stack-based buffer overflow. I want you to draw the stack. So I want you to have a piece of paper and pen with you. And also starting from next week, I also want you to have the virtual machine or the hacking environment ready. You can use the virtual machine I provide, or you can set things up by yourself. You don't have to use the virtual machine, which is just a regular Linux box. And I installed some tools there, that's it. For everything in the class, the recorded lectures, the lecture notes, homework, everything, you should be able to find them on my website, this class website, before the class, and the homework usually after the class. And this will be almost like a 3-hour session. And uh, I don't think I will keep talking for 3 hours. So I will give a lot of lectures, and also we will do some hands-on uh, hands-on labs during the class. That's why I want you to have that a virtual machine or hacking environment ready. If you haven't already, please also join the Slack channel I have there for graduate students. I have a private Slack channel, and then there is a public channel. If you don't know what that is, you can ask that in the chat box. Someone can post that in the thing, or you can email me later. And also, since this is like a 3-hour session, feel free to interrupt me if you have any questions. You can drink, eat as you want. I don't really care, as long as you can focus on the class. That doesn't really bother me. A little bit about myself. My name is Zeming. I am an assistant professor at the computer science and engineering department. I direct a research lab of my own. I call it Cyberspace Security and Forensics Lab, or Cacti Lab. Um, Basically, I lived in Arizona for many, many years, so I call everything cacti. Um, so by the name, you can see that we are interested in all kinds of security problems, not necessarily only just the system security. I have been publishing papers in all kinds of security domains, including system security, software security, network security, usable security, all those. But right now, I have a quite small research lab. We only have 2 PhD students, 2 master students. So right now, we're just focusing on system security. But in the future, we probably will revisit other security areas as well. Is there any questions? No? Okay. So this is my email address, my website, and also my lab's website. If you are interested, you can take a look. Um, the best sending me, shooting me an email. I usually reply email really quick. And also for this class, we have Slack channels. So other students probably can also help you answering a lot of questions on the Slack channel. Um, since this semester we're doing everything online, my office hour is also online. So if you want to talk with me, just send me an email, then we can schedule a meeting. For graduate students who are taking this class, usually I can always meet with you. For undergraduate who are not really taking this class, I cannot promise. If there are too many requests, I probably cannot do that. If you really enjoy this class, it means you are probably the guy I'm looking for my research lab. If after this class you really like what we're doing in this one, then shoot me an email. If you want to work on system security, do some research with me, doing some real world hacking. So every week this semester, we will meet at this URL from 5:20 to 8:10. It's quite long, almost 3 hours. I can promise you that this class is very interesting. It's not boring. But of course, no matter how interesting the materials are, no one can literally listen to me for 3 hours. So in those 3 hours, we will not only have lectures, but also many hands-on practices. And also in this class, I will also do a lot of demos here and there, and I will also class. This class is listed as a graduate level class 610. So far, I believe there are 13 or 14 students registered for this class. And those students, they are taking this as a 3 credit class. And these guys have been invited into this private Slack channel. And we can ask questions, discuss homework, also know each other. And also for the first time, I'm also making this class public to everyone in UB, especially I advertised it in the computer science department. I send an email to the undergraduate student mailing list. So I'm very excited to say that there were actually more than 100 undergraduates send me an email saying they wanted a link. So I don't really know how many people are here right now. Oh, there are 48 students right now. So probably means there are 30 undergraduates online right now, 35 or something like that. So thank you very much for showing up. Like I said in the email, please treat this as an open hacking seminar. You can just come here to learn how to hack, how to crack software. You will not earn course credits for this. Um, so technically, you can come and leave anytime you want. You don't have to do the homework. And in fact, I will not be able to grade your homework if you do. But you will have access to the answers. You will have access to the homework. And also, I create a Slack channel for you guys to discuss. And also, I can answer questions there for you. So basically, if you just want to learn how to hack, especially at binary level, you are very welcome. So this is kind of like the introduction course for my hacking group, Cacti as well. So don't be afraid. This class, even though right now is a graduate level class, I will make it very self-contained. I have seen people with much different background. I'm talking about computer science background doing hacking. So even some high schoolers, they can be really, really good hackers, and they can get into research very fast. And also we plan to do all kinds of CTFs in the future. And this can serve as the introduction course. And I will send you guys the CTF information in the Slack channels that you can join if you have time. We will play under the team name Cacti. Okay, so this class is all about hacking binaries. At the end of the class, you should have a good understanding of the theories, principles, techniques, and also tools used for binary level hacking and also hardening the systems. We focus on binary code, or we call it machine code, which means we will not discuss web hacking in this class. Web hacking or web security is a big area itself, and I'm not offering that class. I believe another professor, um, Wei Han, she probably offered a web security class last year, maybe. Um, so, browser is like the operating system for the code from web, and browser is huge right now. So it has its own ecosystem for hacking everything. It's quite different from a binary. Um, and in this class, we will mainly use x86, AMD 64 as examples, as the example platform. We will not use much like ARM architecture, MIPS architecture, but the theories, the principles behind them are actually very similar. So you will study in depth binary reverse engineering. You will study vulnerability classes, how to analyze the vulnerabilities, how to develop exploits, share code to attack those vulnerabilities. You will also study some defensive solutions to study at the binary code level how it works. For a lot of defensive solutions, they could be deployed at OS level, they could be deployed at the compiler level. For this class, we mainly analyze how they work. There will be no task or experiments for you to, like, let's say, develop a compiler module to implement some kind of defensive solution. That will not be covered by in this class, but probably will be covered in my future class. So basically, you will understand how to crack and also protect x86 and the AMD 64 native software. My main research area right now is actually mainly in embedded systems, such as Cortex-A, Cortex-M architecture from ARM. So they are a little bit different from x86. But for this class, I still choose x86 because x86 is still the most widely used hardware platform. Most binary hacking is still in this platform. Many new attacks were first discovered on this platform, then applied to other platforms. And it's also the most accessible platform for you. All your laptops is x86 or AMD 64. I don't believe any of you are already using an ARM-based laptop. Your phone is obviously ARM-based. Your what's that? Your touch screen, whatever. That usually is ARM-based. But your laptop, desktop are still x86 based. Also, like I said, the principles, the techniques you learn from this class obviously apply to other platforms as well. The key to success in this class is to get your hands dirty by just hacking. All the examples I gave in the class, I want you to do them by yourself. The homework, I want you to do it by yourself. I will also provide some other resources to you, and you can do all kinds of CTFs by yourself and learn how things work. So there is no shortcut, just get your hands dirty. That's super important. A little bit different from what you, for example, to learn hacking, you can just do CTF. Why do you have to take a class? The difference is in this class, I will cover a little bit more theories, principles. So it will be a more systematic way for you to learn hacking. and we cover almost um, all the software vulnerabilities I can think of. Okay, so next, let's do a quick survey. So because there are, right now, there are 51 students here, let's do a quick survey to say which year of undergraduate and graduate you are in. And also, I want to know a little bit about your background. It's not like they are required, but I just want to know. So I just launched the survey. Do you guys see it? Can you guys see the survey?
Yes.
Yes.
Yeah,
Okay.
we can.
Then um, you can fill in.
Professor, what about we can't choose nothing as an option?
Sorry, I cannot hear you. It's breaking up.
Can't we choose nothing as an option? Like none of the above?
Which one? Which question you're talking about?
I'm talking about the second and the fifth question.
Oh yeah. I think I made a mistake there. I think you can choose nothing, right? Or I made a mistake. You probably cannot choose. It doesn't really matter. You just select whatever there. Yeah. Sorry for that.
There's no option.
Yeah, I think there's no option for nothing. Yeah. Okay, I will give you guys 30 more seconds. Okay. I got almost a 40 replies so far. Looks like there are 13 students in graduate school and then 10 freshmen, several sophomore, junior, and senior. That's very interesting that we'll have more freshmen than sophomore and junior here, which is a great thing because I don't believe hacking uh, is something you need a very solid math background. You have to do calculus first to take this class. You don't have to, so which is good. And if this class can expose you to hacking earlier, that's exactly what I'm trying to do. Okay, very good. Let me take a screenshot of this so I know. Okay. Okay, so today we will go through the class overview, logistics. Before we dive into some background knowledge, you probably have picked up several pieces of background knowledge from your previous classes, or just pick up something from your programming projects or hacking experience. But please bear with me since I always want to make the graduate level class also self-contained, so people from different backgrounds can learn. Uh, Having said that, I will cover most hardware and operating system knowledge you need for this class, in this class. And today we will briefly talk about compiler, linker, loader, um, the x86 and the AMD 64 architecture and their instructions, the Linux file permissions, what are setuid programs, the memory maps of a Linux process, and also what are system cores, and also what are environment variables. The reason I talk about those, that's because we are going to use them in next week's hacking. In the future, there may be more background before each class, especially for the cache side channel attack. We will spend a lot of time talking about how cache works. Otherwise, it's basically impossible to understand the cache side channel attack. And also today, I will show you some reverse engineering tools. Some of them I already, some of them it comes with Linux. Some of them I put them in that Linux virtual machine. Okay. So there is no prerequisite for the class. I didn't set anything there, but the C programming language is really important. If you are not very familiar with C, um, you probably will struggle in this class. Even if you probably will not do a lot of coding in C in this class, you will read a lot of C code. You will read a lot of disassembly code as well. If you are not very confident with your C ability, please read this book, the C programming language book by the people who invented the C programming language. So you can easily find this book online. You don't have to purchase one, or you can find it through UB library online, I think. You can keep reading the book and also taking the class at the same time. Or other security and system classes you have been taking can also help you. For example, a lot of people said they take Introduction to Information Assurance. So you understand the basic principles of security. You understand what is the CIA, right? What is confidentiality, what is integrity, availability. And this class will be much more, what should I say, what more lower level than that. Sometimes at the so lower level, you do not realize what you are doing is about integrity. What you are doing is about confidentiality. But all of what we're doing fall into those security uh, goals, those categories. Okay. So the security classes, they are not really required. The skills you will learn in this class include reverse engineering. We were using all kinds of tools, especially object dump. I will try to teach you guys use the most accessible tools, the one which is free, the one which is everywhere you can use it. For example, like object dump. There are much more advanced tools like IDA Pro, like Ghidra. I actually installed Ghidra in the virtual machine for you. They are advanced tools. Um, they are very intelligent, very smart tools, but sometimes I don't necessarily want you to rely on those tools. I only want you to rely on the simple tools so you can understand how everything works. Then later, you can use those more advanced tools. We probably will not use IDA Pro because I don't feel we need to use IDA Pro. Ghidra is already quite good. IDA Pro is another commercial tool. There is a free version for it, but the free version is not as powerful as the free Ghidra version. I don't think Ghidra has a commercial version. Ghidra is all open source. IDA Pro is very good. I've been using IDA Pro to do manual analysis. I've been developing plugins for IDA Pro for some automatic analysis before. It's a very good tool. It's just super expensive. My lab used to have a floating license, which is like 2K US dollars. This is actually the first class I teach at UB. I just moved from RIT, so I don't have access to that license anymore. So even right now, I'm not using IDA Pro. And I guess probably some of you already heard of those tools and maybe used them before. So in the first 2 weeks, there will be several experiments, several labs for you to get familiar with those tools. And we will mainly use GDB for debugging. And in the virtual machine, I already installed some plugins for GDB to make the debugging GDB less painful. But if you want to use the vanilla GDB, it's okay. I've been using vanilla GDB for many years. You just need to remember all those commands. I installed several tools like PwnGDB there for you to make things easier to view information. We will take a look later. Actually, the most important skill for you to survive in this class is the same skill you use for any research. Basically, you need to be good at Googling things, finding materials to read, learn things by yourself, and getting your hands dirty. So those are the most important things. The lecture is only 3 hours a week. How good you are a hacker depends on after the class, how many hours you spend on getting your hands dirty. So we will mainly cover 8 topics in this class. You will learn many vulnerabilities and also learn how to develop exploits for those vulnerabilities and some of the state-of-art research on those topics, such as new advances in attacks and also um, some defense solutions for it. Those 8 topics are the first one is a stack-based buffer overflow. Starting from next week, we will spend a little bit more, maybe more than 2 sessions on that. Then we were talking about the existing defenses against the stack buffer overflows. So together we will spend 4 weeks on that. After that, we will talk about how to develop share code, what you need to consider to develop share code. After that, 1 week on format string vulnerability. After that, 1 week on heap-based overflow. After that, 1 week on integer overflow. Then we will talk about the very interesting return-oriented programming, or we call it ROP. So actually, when we talk about stack-based overflow, we were already touched something about ROP. We were talk something like a return to libc attack, which basically is a ROP attack, but it's not a very generic ROP. And then the last topic is a little bit different. The first 7 topics, I would call them memory corruption attacks. Basically, we're trying to attack something in memory. If you say this, view this from a computer architecture level, we're attacking something in the memory at runtime. Then the last one, the last 2 weeks, we will talk about cache sidechain attack, which is a bit lower level than memory. So cache is part of the CPU. It's not really the memory. Memory is not part of the CPU. Then we will talk about the infamous meltdown and spectrum attacks. Those attacks relies on cache side channel attack, but they're a little bit more than cache side channel attack. So you notice that I used 2 different terms here. The first one is called vulnerability, and a vulnerability is basically a weakness in a software or hardware system. It's probably a weakness brought there by design, but no one knew that was a weakness. Sometimes people design that, know that's a weakness, but they don't think about how this can be exploited, or sometimes they think it's not worthwhile to fix that problem. Um, then the other term is called exploit. So an exploit is an attack that leverage that vulnerability. Um, so those 2 terms, they have different meanings here. The hacking environment we're using in this class is just a regular PC. For 95% of the class, it doesn't really matter if you use Intel-based PC or AMD-based PC. But there are, for the last class, the last 2 classes, the cache one, there probably are several cache side channel attacks labs. You have to use an Intel PC because ARM basically doesn't have that vulnerability. There is no vulnerability in ARM CPU there in the first place. At OS level, we will use Linux. That's why I provided you with this VirtualBox image, and you can download. It's only 5 GB or something, I think. This is just a regular Ubuntu box. I installed some tools there you can use. You don't have to use that one. It just makes your life a little bit easier. You can set up everything in your Linux box or but if you want to set up everything in Windows, I don't think I can help you. It probably will be a little bit different. I cannot help you there. Anyway, you are not required to use that. Those are several tools I already installed for you there. The PwnGDB, the GDB Peta, which is like a Python plugin for GDB. Then also there is the National Security Agency GIDRA, like a disassembler there. We will take a look later. So this is the VirtualBox, the virtual machine. You can say the username you can log in is just a hacker. The password is just a hacker in reverse. Install there. Later, I will show you how we can use it. But like I said, I also sometimes I want you to rely on more, simpler tools, not advanced tools like this. This is a graduate level class, so there will be a lot of readings. There will be a lot of homework. To be honest, I'm not sure how much time you will spend on the homework. For some of you, those could be quite challenging. You spend more time there. For some of you, it might be a little bit easier. But for graduate students who are taking this class, you have to submit your homework every week before the next class, because we will discuss the homework at the beginning of each class. We will discuss how to hack those binaries, how to basically most of them are hacking labs. I will give you like 10 minutes. If you submit your homework 10 minutes after the class starts, you can still get like 70% of the points. But after 10 minutes, you will not get anything. For other students, you will not be able to submit this, but you can discuss in Slack channels, and also you will get the answers, and we will discuss those homework in the beginning of each class. So, um, so my suggestion to graduate students is start early. Some of the homework could be quite challenging, so start early. Don't wait until the last minute. Okay, so there will be a lot of hacking labs for this class. For each hacking assignment, you need to submit your exploits. You need to have a simple write-up, just several sentences. The purpose is by reading those sentences, I will know you are not cheating. You actually did this. Also, I also needed to say some screenshots. So when you do the hacking, you just take some screenshots to show it works. As a homework, they were all in Word document. You can just post everything in that Word document and submit on UB so UB for me is just the place where we submit the homework. Everything else you can find on our website. So the write-up, just several sentences, briefly discuss how you solve the challenge. If you get help from someone, you can also mention that, who you worked with to finish this one. But I don't want anyone to directly share exploits. No matter you are undergraduate or graduates taking this class, I don't want you to share the exploits online. I don't want you to directly share the exploits to others. You have to figure the exploits out by yourself. I encourage you to discuss, but you share things online, you may face some kind of a penalty. So for the exams, there will be two written exams. One is the midterm, another one is the final. So those are not open to the undergraduates. And I actually haven't decided yet if this will be open book or asynchronous. Let's see how it goes. We are still like 2 months away from the first exam anyway. And also in the last class, we will have an in-class CTF. So the CTF will be 1.5 hours to 2 hours. So there will be several challenges. This is also only open to graduate students. I probably can open it to undergraduates after the class, but this is kind of like part of the final. So that's first we're only opening it to graduate students. Then there will be several challenges. You crack the challenges, you get some flags, you get points. I probably will have like 5, 6 challenges there. So it's not like I expect you to finish all of them. Some of them, if you have been really good during the semester, you probably can finish them in 2 hours. But it could be some quite challenging for everyone to finish that in 2 hours. Don't worry about the grades for too much. Usually I curve it at the end. Depends on um, depends on how much I think how good you guys are at that point. So here is the grades. Like I said, I may curve them at the end, but right now we will follow this. 2 exams, each one 100 points. Then there will be 14 homework. Each of them will be 45 points. So as you can see, that will take up to 600 points. So if you do really good in the homeworks, you don't need to worry about failing the class. And also there is in-class CTF, and also I will check attendance. Obviously this is for graduate students. Oh, by the way, let me send out the link for attendance check here. Okay, you guys can see the screen here. So let me just do. Where is chat? Okay, so I send you guys the attendance check. It's just a Google document. So if you are a graduate student, just put your name here. This is required. For undergraduates, you don't have to do it. You can voluntarily do that. Okay, cool. Let's go back to the slides. I think someone asked a question online here. Let's see. I need to answer that. What's the password for the VM? I also said that. Okay, any question here? Oh yeah. So if you want to use your own environments, that's totally okay. Like I said. Okay, go back to the slides. Okay. Then about the academic integrity, obviously this is super important. So I want to emphasize it, especially before we dive into hacking. Okay, discussion is encouraged. You should discuss with each other, but you cannot directly share your code, your exploits, or post them online. You should be familiar with policies at the different levels, college level, university level. You should be expert for that. I don't really know how many policies are there, to be honest. But in short, I have zero tolerance towards academic dishonesty. For example, if you cheat in your homework, you cheat in lab or exam, you probably will get an F. For the item you cheat on, for sure you will get a Z. You will get a 0 for that, but it's possible you will get an F. So I have failed many people in my previous classes before. To me, it's very simple. You come here, especially for undergraduate, you come here to learn something interesting. There is no reason for you to cheat. The same thing for graduate students. As long as you spend enough time, you should be able to get the grade you want. Because I'm here to help you, and also other students are here, they can help you. There is no reason for you to cheat. Okay. Besides that, because this is a hacking class, I want to talk a little bit about ethical hacking. We don't we teach things that can be dangerous. I do not think it's dangerous itself, but it can be dangerous, depends on how you use it. So don't attempt to violate any law. Okay, if you discovered some real world vulnerabilities using the knowledge you learned from the class, that's great. But after you find that, you should report that vulnerabilities responsibly, and you can get credits for that. So you should be a white hat hacker, not really a black hat one. Okay. Um, basically that's it. Okay. So attendance check, I already sent you guys the link, so we will skip that. Okay, so next we are going to move to the first piece of the background knowledge, compiler, linker, and loaders. So we will take a look how to compile a C program into a binary and run it on an operating system and also run it on top of the hardware. C obviously is a high-level programming language. It cannot directly run on any machines. So we need a compiler to convert it into an executable code, which consists instructions of a specific machine. So when you have a C code, you can compile it into binary run on ARM architecture. You can also compile it into binary run on Intel architecture. Obviously, the C code is the same, but the compiler is different. In this class, we mainly use Ubuntu Linux or just Linux as your host operating system. We will use GCC as your compiler. And there are usually 5 phases from a C program run to a process running on the OS. 4 of them are part of the compiling. We first start with a C program. It can be a program.c. Note here, we're talking about one C file. We're not talking about multiple C files. So for the first several phases, it applies to each C file. So the C file is basically source code. It's a text. Then it will first go through the stage called the pre-processing. In pre-processing, a lot of first of all, C program, unlike any other programming, there are comments. Comments are for humans. Uh, Compilers don't need them. So the comments will be removed. And also macros will be expanded. Included files are also inserted into the C file. So in the C file, you may include some .h file. And at this stage, they will be inserted into that C file. And maybe if you are C programmers, you probably know that you can do some kind of a conditional compiling using directives like if def, if if df, something like that. So if you define something, the compiler is supposed to get this part done, otherwise other parts. That is also the pre-processing part. So using GCC, you can actually print out the output of all those steps. And usually, if you just use the default parameters for GCC, you will just get from .c file to the binary file. You don't get anything in the middle, but you can get that. So that's what I'm going to show you right away. So after these steps, the .c file actually becomes .i file, which is still text. It's just the included files, the .h files are inserted there, the macros have been taken care of. Then after that, we will actually compile this .i file. Well, this .i file may not exist on hardware. It may be just a data structure in memory. Then it will compile into a assembly file, assembly code. So even after this step, this is still text. This is not code. It's not a machine code. It's not binary. So the assembly code usually we use .s file there. Then we use another another compiler, which we call assembly. AS is the tool usually we use to generate .o file. And the .o file is actually binary file. Usually we call it object files. And if you have multiple object files, because you have multiple .c files, you generate multiple objective files. then you can link them together into a final binary which you can run on your operating system. And that is an executable object file. And this is still a file, it's not a process. It's not running anywhere on your machine. Then the operating system, there will be loaders. It's kind of some kernel code where load some file, some binaries in your hard disk and load them into the memory and give the CPU, this piece of code the control of the CPU. Then this piece of code will start running, and we call that a process. So this is basically the steps from a C program to a process. There are other programs as well. Not all the programs are compiled. So this is how we compile a program. There are programs that use just-in-time compiling. There are programs interpreted. Obviously, those will be quite different. In this class, I think we mainly cover things that are compiled, batteries. So this slide shows a little bit about the loader. So in Linux, we can consider loader is like the handler of the system call execve. So basically that is the system call to execute some binary file from the hard disk. And the handler of that system call is basically some kernel code. And that is just the loader. So the loader is obviously part of the OS kernel. It to execute a new program. First, it validates if the request to start this process is valid. You have the experience that you try to start a program and the OS tell you you don't have permission to do so. So that's because the loader is checking if you have the permission. The user has a permission to run the program. Okay, if the user has a permission to run the program, the loader will copy the program image from the hard disk into the main memory, or not necessarily hard disk. I mean, talking about from storage, secondary storage to main memory, because the CPU cannot run things directly from hard disk. If we're talking about flash, we're talking about embedded systems, the CPU probably can run things there. But for x86, the platform, usually we cannot do that. It also, the loader has to set up the stack for the process. Stack is a very important concept here at OS, and also very important for hacking. For C programs, you will say later, or C functions, they will have some stack operations at the beginning and at the end for C functions. That's why as long as you call a C function, you have to set up the stack before that. So the loader will help the process to set up the stack. It will also copy the command line arguments onto the stack. So the program can access those command line arguments. For example, you do a ls-al, right? You are giving, so ls is obviously a program, a binary, and you type this into a shell. And you are giving a parameter -alz. So what happens is the shell itself will fork itself. So it will be two processes exactly the same, which resembles the shell. Then the child process, we're actually using this system call execve to execute ls, which means retrieve ls from the disk, the file ls from disk, load into memory. Then when you run ls, the ls has to know what parameters the user has been giving me. But the parameter was actually providing to the shell. It's not providing to the program. So the loader will also copy that command line arguments, which is -al, to the stack of the program. Then the program can go. This is now the parameter the user gave me, the arguments the user gave me. Also, the loader will set up those registers, many the stack pointers, and also something else. And the last step is to jump the loader will yield the control of the CPU to the new process by simply jumping to the program entry point. And the program entry point actually is not the main function. So when you write a C program, you always have a main function. And to you, that is the entry point. But for that battery you actually generated, that's not the entry point. Usually the entry point is a function called start, or maybe a function called uh, something lib main. I don't remember exactly what's the name of that function. But basically, the start will call that function. That function will call other functions, probably set up things, and eventually that function will call your main function. But to you, because you are the developer, you feel the main function is the entry point. But to the binary, it's not. Okay. So here, let's take a look at this example. Any questions so far? Is everyone doing good? Okay, everyone's doing good. Cool. Okay, so here let's say a very simple example. Um, so most of the examples in this class, I just developed them. They are very simple anyway. So we have two .c files in this project. You have access them online. Uh, One, we have an add.c file, which has a function add. It will add two integers together. Obviously, I'm not doing any checking here. So obviously, this could be an integer overflow variability there, but the point right now is not to exploit the integer overflow. Then we have a .h file, define this function. We have a main function, as you can see. It just includes several libraries and also includes the add.h file. And the main function here is just the prototype you are familiar with. So the main function return int. Usually 0 means everything is good. If it's not 0, it means something is wrong. Then the first argument here is called argc, means the count of arguments. So it's an integer. It tells the main function how many parameters, how are there, including the program itself. Okay. Then it has a array of pointers. So basically, the array have multiple pointers. Each of them points to one string. Okay. Then we have int. We have two local variables here, a and b initialized to 0. Then we check if the argument is 3. The number of arguments are 3. If not, then we will just print out the usage and return 0. And we will also, so after that, we will change the first argument to an integer, change the second argument to integers, and we will just add them together using the add function. So if we just, let me see, where are we? If we just try to compile this, okay. Code, let's say this is add, okay. So I already shared this with you. As you can see that I have a make file there. Let's take a look at the make file. So as you can see, when you do this, you don't have to type the command here. You can just use the make file. The make file, I defined that we are using GCC. We are giving the GCC the WO, which means we want to show all the warnings. We also have save temps. This will save all the intermediate files I just showed you, like the .i files, .s files, .o files. We will show all the files here. Then -m32 means we want to compile this to a 32-bit program, because the machine we're using right now, most of the machines, well, all the machines we are using are 64 bits. And we want to do 32 bits and 64 bits, so you can compile it into 32 bits or 64 bits. This one shows the optimization level we want to use, and this one shows those are the source files. Then the output is a function called add. So when you compile this, you don't specify the name of the header files. For GCC, you just need to specify the location of the header files. In this case, the header files are in the same folder, so we don't need to do that. So let's do a make clean, quick clean here. So I cleaned up everything. Let's see what we have here. So right now we only have those two .c files, .h file, and a make file. Then we just do a make. So do the 32 version. This, I think make is a 32 bit version. You can see here. Okay. Now you can see. Now we have many new files here. We have the add file, which is blue. If you do a file on add, it will tell you this is a L file. It's 32 bit. This is dynamically linked, and this is the interpreter for it, and the hash value for it. And also you can see we have .i file, .h. .h is kind of source .i file, .o file, and .s file. Then let's do a .i file, and you can see .i. This is just a text. So we do a cat here, and you can see. So this is actually from the and .c file. So this is the .c file you have here, right? This is C file. And after the pre-processing, after you get this .i file, which you can see the compiler will add some comments here and there to tell the later stage of the compiler how to deal with this. Then after this, we get a and we can get the assembly file. And this is assembly file. And from the assembly file, you can see there are instructions. So those are instructions. So move, but they are not binary. They are still text. There are returns, there are and, then there are some protection here, you can see. CFI actually is control flow integrity. It's one of the security features. You can see compiler automatically add those security features there. Okay. For some of the examples we will use in the future, we will disable those security features. Otherwise, it's extremely difficult to exploit those vulnerabilities. Then after that, what we have .o files, right? Let's do file .o file. If you do a .o file, you can say .o file is also an L file, the object file. So the .o file, there will be two .o files because there are two .c files. Add.o, main.o, and they will be linked together to generate the final binary, the and. So if we run add here, it will give two parameters. Okay, we'll just do this, then it will give us the answer. So this example shows how the C compiler works. Let's go back here. Like I said, this program itself has an integer overflow because this integer is 32 bits. This integer is 32 bits. By adding them together, we can get something 33 bits. But we are only storing it in another 32 bits result. So there will be integer overflow. Okay, next we will go through some background of the x86 architecture, which is still the most widely used architecture for laptops, desktops, and all sorts. You need to remember how big data is on this architecture. Byte is 8 bits, word is 2 bytes. D word means double word means 32 bits. So this could be quite different. You know, different architecture use them for different size. So if you approach another architecture and you say the word D word, you need to be careful. You need to check the document to see how big a word is. For example, in ARM architecture, byte is still 8 bits, but word is 4 bits, 4 bytes, sorry, 4 bytes. So they don't use the word D word anymore. Then we have quad words for 8 bytes, and also double quad word for 16 bytes. So you need to remember this. Also, you need to know what is endianness. Endianness is the ordering of bytes of a value in the computer memory during transmission uh, during or execution. So it's an ordering of bytes of a value. So if that value is only 1 byte, then there is no ordering. It doesn't really matter. But if the value is bigger than 1 byte, let's say the value is a D word, it's 4 bytes, something like an integer here, it's 4 bytes. Then how do you put that 4 bytes in the memory? Obviously, you have 4 bytes, you can put it into 4 different locations, then there are many ways to do so. Okay, the most two popular ways is called the little endian and the big endian. Likely, the platform usually I work on, they are all little endian, so makes things a little bit easier. So in this case, the system we're using is just little endian. I think MIPS is big endian. No, maybe not. I used some big endian system before, but I don't remember which one. Maybe some kind of MIPS you can make it big endian. ARM you can actually choose, but most people are using little endian. So when we use a little endian, it means the least significant byte has, or let's say it is stored at the lowest address. Let's say if we have the value this, it's a hex 7856333412, right? So this is a big value. This is a big number. So the most significant byte is obviously 78. The least significant byte is 12 in hex. If we store this in 4 bytes in the memory address 0, for a little endian system, what we do is the least significant bytes always the address, which means 12 in hex were stored in address 0. And then 34 were stored in address 1, 56, address 2, and 78, address 3. That's how we store it. For big endian systems, it's actually reversed order. The least significant byte has the highest address, but we're not using this system, so we will not go through that. But as you can see that, how many possibilities you can choose here? If you design a system, you design a new endianness. Basically, if it's 4 bytes, there are not only just 2 choices you can make. You can do 4 times 3 times 2 times 1, right? So basically, there are 24 choices you can use. This is combination, right? So 42 designs you can use. But some of the designs, actually, people in history used them before. Some of them are called medium endian. But I don't know the point. I mean, storing things that it's a little bit weird. That doesn't make things faster. It doesn't make things more compact. So there's no reason to do that, basically. So right now we're just, most of the systems we're using little endian here. For x86, there are several base registers. You'll need to remember those base registers because you will need to read the disassembly code. And there are many system registers as well, but for this class, we're not doing much kernel level hacking, so we were not talking about those system registers. First of all, there are 8 general purpose registers. There is one 32-bit flag register. So you can imagine at the very early version of Intel CPUs, it's just called flags. There is no E. So those are 16 bits. Then they extended to 32 bits. That's why there is a E. E means extended. So extended flags. Then there's another 32-bit instruction pointer register, or we call it EIP. So that one points to the next instruction the CPU is going to execute. Since it's only 32-bit, which means basically it just stores the address of that, right? So which means the address space in the 32-bit CPU is also 2-bit, which is 4 GB. And there are some other general purpose registers, which is not very important for this class. Okay, So here we have that 8 32-bit general purpose registers. They are EAX, EBX, ECX, EDX, ESX, ESI, EDI, ESP, and EBP. So actually only those 6 you are usually using as general purpose registers. So those 2, we have some very specific usage for them. They are associated with many different many instructions. So as you can see that, how do you remember this? First of all, you have A, B, C, D. Okay, those are 4. Then you have S. S is like source. I kind of index. So this can be used as a source index. Then you have DI, which is a destination index. So they are all 32 bits. That's why they start with E, ESI, EDI. And for some of those registers, you can access part of it. For example, you can access the least significant 8-bit of the EAX register directly. You just use another alias for it. You call it AL. Or you can use AH or AX to access this part. So if you use EAX in your assembly code, you are accessing this part. If you use AL, you are accessing this part. AH, you are basically accessing this part. So this is backward compatible to very old Intel CPUs like the 8086 or 8080. So 8080 is 8-bit CPU. They only have AL, right? So they extend this over the 30 years. Now we get something like this, actually a little bit, even bigger than this. You can see later. Okay, so those are the basic general purpose registers available on this platform. That's it, those 8. The ESP is very important. It's a stack pointer. It points to the top of the stack. Then we have EBP points to the bottom of the stack. We will talk a lot of those next week, next several weeks actually. Okay. So, I already talked about this. Then we have the or this is just a one register, 32 bits, and there are many status flag to show what is the program status. For example, there's a carry flag, there's a parity flag, there's a 0 flag, there's a sign flag, and the instructions may behave differently according to those flags. Okay. The EIP register is not really a general purpose register. It holds the address of the next instruction to be executed. In the Intel architecture, there is no instruction for you to directly access or put data into this register, but there are clever ways to do so. Okay, so this is a bigger picture of all the registers available on x86 and also 64. As you can see that here we have those EAX, EBX, ECX, EDX, and ESI, EDI, EBP, ESP. Okay. Then you can see there are other registers called, so EAX is 32-bit. In the 64-bit version, it is extended again, so we call it RAX. And in the 64-bit machine, we have many have R8, R9, R10, R11 to R15. Those are new registers that were not available on x86 machines. They are only available on 64-bit machines. You can also see here we have many registers named CR, right? CR, what is it? I think maybe it stands for configuration register. Important configuration registers. I'm not sure if C stands for configuration. Some of them hold the address of the breakpoint. Some of them hold the address of memory tables, something like that. And there are many of those. by configure. So as you can see, operating systems have to configure those registers to make things work smoothly. And on the left-hand side, we have a lot of here. Okay, I guess it means multimedia or something. So those are for float point, multimedia calculations. If you are as old as me, you probably remember when I was in high school, Intel introduced something called MMX, multimedia, um, to make gaming a little bit faster. So those are some of them were introduced back that time. And here we have some segment registers. We will use a little bit of those registers in this class, but nothing to be afraid of. I will just tell you what they are for at that point. For example, we have a CS, SS, DS. Um, the name is like code segment, stack segment, data segment. But right now, um, we use it for different purposes. So the name stays there. The name is a little bit obsolete sometimes. Okay, then we also have other, those are global descriptor, translation register, interrupt, uh, descriptor, table register, I think it's. Okay, as you can see, those are also used by the OS to set up the system. Also, we have DR. D obviously is debug. So those are debug registers. So if you are developing a debugger, probably that's what you need to use. And we have the flag registers, flags, E flags, and the 64-bit of the R flags. Any questions there? Any question at this point? I do not get any feedbacks here. I'm not sure if this is too boring for you or what's going on. Okay. Okay, if it's good, let's move forward. Well, the first class is a lot of a background, so it's probably not as exciting as the second one. So the second one will be quite exciting because you were actually doing hacking starting from the second class. Okay, so each instruction in this platform follow this kind of a format. First, we can have a label for it, which is optional. Then we have the name of that instruction. Then the instruction can take up to three operands. Sometimes it's just zero. There's no argument basically. And each operand is basically an argument. It can be an intermediate value, just a number. It can be a register, or it can be a memory address. And that memory address can be specified by a memory or even by some kind of a calculation. So each operand is either a source or a destination. So a source obviously can be an intermediate number, it can be a register, can be a memory address, but the destination cannot be an intermediate value. It can only be a register or a memory address. Here I have 4 example instructions. The first one is called HLT. As you can see, it probably means halt, right? It means stop the CPU. And when you execute this instruction, the CPU will stop until some external interrupt is fired. And for this instruction, obviously, you don't need to have any argument. There's no argument. Then the next instruction is INC. As you can see, it probably means increase, right? So increase, you can increase something. You can increase a register's value. If the value is 0, you execute this one, you get a 1. Or you can have an addition, so which take 2 arguments. So one of them will be used as the source and destination in this case. So because we're doing addition, there will be 2 source, 1 destination, and one of them is used as the destination and the source. Then we have IMUL. I means what? I means signed, integer. Yeah. So MUL means multiply. So basically we can multiply several things together. For example, here we have this could be a destination register, another source register and another constant. So we times this one with this one, then put the value back this one. This is so this is a instruction with 3 operands. And at the assembly level, we have 2 different syntax. Uh, some of us are familiar syntax. Most of the tools you can generate, um, you can choose which syntax you want to use. I usually, ooh, can anyone hear me? Looks like my internet is not very stable. Is everything good?
I
We
can
can
hear
hear
you.
you now.
Okay, cool. So for AT&T syntax, um, so basically the instructions, they fall into several categories, into data movement instructions, arithmetic or logic instructions, and also control flow instructions. Then for AT&T syntax, to specify a register, you have to use the percentage sign here. So if you want to use EAX, you have to specify a percentage sign to show, hey, this is not just a string. This means the register. And for a memory address, you will put some value into this parenthesis. Okay, you can put a register here. If you see something like this, it means we are talking about the memory location, which is specified by the register EAX. We're not using the value of EAX directly. We're using the EAX into the memory and get the memory value. Okay. So Intel syntax is quite similar. If you, I actually for the homework, I gave you 2 readings to do. One is the Intel syntax, one is the AT&T syntax. They are equivalent. Okay, they are not machine code, they are assembly, but they maps to the same machine code, so they are equivalent. Just the syntax is a little bit different. The tools we are using, for example, the GDB, the object dump, most of the tools, they automatically show AT&T syntax. But I think the DDraw automatically show Intel syntax. So you can either pick a syntax you like and configure those tools, or you can be good at both syntax, then switching between them is not a problem. Either way is fine. So most of the examples I'm using here, I will use AT&T syntax because most of the tools we're using AT&T syntax. So in AT&T syntax, for an instruction, for example, we have a move instruction. The first argument is the source. The second argument is the destination. So when we move parentheses, percentage sign, EBX, then EAX means we are moving the value at the memory location, which is specified by EBX, to the register EAX. So it's like move this one to this one. For Intel, it's a little bit different. Intel, the first argument is actually the destination. The second argument is the source. That syntax is consistent with some other platforms. For example, ARM also uses the destination as the first argument, but it doesn't really matter. So this instruction means load 4 bytes from the memory address in EBX into the register EAX. So in EBX, what we have is just the memory location, its address. What is changed after this instruction is the register EAX. Then the next instruction, the same thing. The only difference is we have an offset here outside of the parenthesis, which is -4 in this case, which means we are moving 4 bytes at the memory. So this 4 bytes is not really this 4. This 4 is actually the offset 4. Okay. So in this case, it's 4 bytes because it's default is this, we're moving 4 bytes. Okay. So this one means we're moving 4 bytes at the memory address, which is specified ESI -4. So ESI -4 will get to that address, so load that address 4 bytes into the register EAX. That's what we do here. Then this one, we're moving CL, right? CL is only what, 8 bytes. So it's just 8 bits, just 1 byte. So obviously we're just moving 1 byte from a register to a memory location. As you can see the parentheses here, then you know that's memory. So we're moving from register to location. So the register is say L, which is 1 byte. So what is the location? The location is specified by those 3 parameters, and we need to take those 3 into this formula. Okay, so it's basically the first argument plus the second one times the third one, and the third one can only be a constant in this syntax. We're calculating the memory address at which is ESI plus EAX times 1. Look at this instruction. You can see this can be used for something like array access, right? So the first argument is like the beginning of the array. The third argument is like the index. This one could be the size of each item in this, right? For example, the size of each item is 4 bytes. Then we can put 4 in EAX, and the ESI will put the address, the beginning address of the array. So this instruction, obviously, if we put a loop around it, then this supports some kind of array operation. This one is similar, just the direction is different. We're moving things from memory to register. And the memory location is from ESI plus EBP times 4. Okay, so here it's like also same as some kind of array operation, right? For Intel architecture, Intel syntax, we're not using parentheses. That's the syntax difference. We are using brackets for it, but we swap the source and destination, but everything else is quite similar. You will find that out in the reading assignment. Okay, then you can see here we are addressing memories. So sometimes this could be ambiguous. For example, we are moving a number 2 to this memory location. So this memory location, the EBX, obviously is 62 bits. But we don't know how much data we're moving here. Well, we can have default, let's say we're moving 4 bytes. So because the number 2, it can be 1 byte, it can also be 4 bytes. It can be 2 bytes. It can be 4 bytes. We don't know that, right? So that's why sometimes you can say instructions with a prefix, like a B, like a W, like a L. So B basically means byte. W means word, which is 2 bytes. And L means long. Long in this case means 4 bytes, right? And we also have Q, 8 bytes. Okay, so if we run this instruction, move to the memory location EBX, it's a little bit ambiguous. Maybe the default one is L, but we can specify it into something more accurate. For example, if we can do move B to then EBX, then this means we are only moving 1 single byte. If we use W, means we are moving 2 bytes. If we are using L here, means this one is actually 4 bytes. Okay. So if you see something like this, don't be surprised. So we already showed you the move instruction. Basically, this instruction copies data item from its first operand. It could be register, it could be memory, it could be constant value into a location referred by the second operand. And the second operand could be a register, could be memory. The memory could be specified by register or some register operations, but it cannot be a constant value. Okay. So for example, move EBX EAX means copy the value of EBX into EAX. So the old value of EAX after this instruction is lost. We don't know the old value of EAX anymore in this case. EBX and EAX have the same thing after this. We can also do move 5 into some place here. So basically store the value 5 into into byte location at this value. So this is a placeholder here value. Okay. Then there are some other data movement instructions. Today I will talk about several that is super important for security. For example, the push instruction, because they are handling the stack. And the stack is a major issue in security. The main reason is we put data on stack. We also put control information on stack. We don't separate those two channels. And so sometimes the machine will mistakenly treat data as control information, and that will trigger some kind of attack. And the push instruction is an instruction that we use to place things onto the top of the stack. So in the Intel architecture, what push does is the push instruction will first decrement the ESP. Remember the ESP, which is a stack pointer register, by 4. Then places operand into the content at that address, ESP. So for example, we can do push EAX, which means we will move ESP 4 bytes to a lower position 4 bytes, then push the value of EAX onto the stack. Remember, stack is part of memory. So basically, we're moving data from register to memory in this case. And the value of EAX, the value of the register is not changed after this. After this, the stack is changed, the memory changed. So what we can do is we can also push constant. We can also push a memory location to specify the value there, also registers. So some of you learned from the data structure class. If you have push, you have pop for a stack. So pop is the opposite operation from push. So we can have instructions like a pop EDI. So this instruction will pop the top element of the stack into the EDI. It will also change the ESP. You can also do a pop parenthesis a register. So it will pop the top element of the stack into the memory. It will not pop into the register. It will pop into the memory. Okay. So where are we? And also for the x86 architecture, another thing you need to remember, I will emphasize many times, especially next several classes, is the stack goes from high addresses to lower addresses. So if you push something, the value of ESP decrease. If you pop something, the value of ESP increase. This is the same for many other architectures as well. ARM also do the same thing. The next instruction I want to talk about is the LEA instruction. It stands for load effective address. The name of this instruction is it's quite confusing. When you think about this instruction, node effective address, you think about, okay, we're talking about memory address. But actually, this is usually used for quick calculation. Okay, for example, we want to calculate this. When we want to calculate the address of some elements in an array, and the base address for that array is EBX. Each element, we are looking for the eighth element. No, let's say each item in that array is 8 bytes, and we're looking for some element specified by the ESI register. Okay, then we want to know what is the address. So basically, we're going to do a quick calculation here. So look at this instruction. The instruction is EAX. Sorry, the instruction is LEA. Then we have parentheses, and we have this. Then we have the EDI. So you know this. What we have in the parentheses is the register used as address, right? So we calculate this. Then you will think we're going to access that memory. But in this instruction, we will not access that memory. We will only get the address of that memory, which is calculated by this. So basically, we're loading the result of this formula into the EDI. That's what this instruction does. You will see this instruction a lot, especially when there are some array operations in the disassembly. There are other arithmetic and logic instructions. Those instructions are easy to understand. If you don't, for example, when you are viewing these assemblies, you don't know those instructions, just Google. Okay, should be very fast. You should quickly be able to quickly understand them. For example, add 10 to EAX. This is obvious. We are adding, so we are set EAX to EAX plus 10. We can also add 10 to the parentheses EAX. Basically, we are adding 10 to a single byte stored in the memory location stored there, right? Then we also can do a subtract or can decrease. Decrease is just subtract one. Then we can do multiply. So here we can multiply a value in the memory content and to the register, then put them back to the memory to the stored. Oh, here the value is stored in EAX, and also we can do shift here. So those instructions um, you can Google when you don't understand them when you do disassembly. Then there are another class of very important instructions are control flow instructions. So what is a register that specify what is the instruction to execute next? Anyone remember? What's the instruction? What is the register for that?
IP.
What?
IP.
Yes, the IP or the EIP, right? So the control flow instructions basically will somehow change that EIP register. For example, we have this jump instruction where basically transfer program control flow to the instruction had the memory location indicated by that operand. So, so if we say address, or we can use a label. So let's do a jump begin. Then basically we are setting the EIP to that location. Just that simple. We're jumping there. Okay. But some of the jumping instructions are conditional jumps. So they are based on the status of a set of condition codes that are stored in that flag register, the E flag. Okay. So the content, the status could include informations about the previous arithmetic operations performed. For example, one bit of the word indicate was the last result was zero, like the 0 bit. It can also indicate if the last result was negative, if it's a subtraction there. Based on those conditions, a number of conditional jumps can be performed. So this is kind of like at a mapping to the C level. This is kind of like the if what should I say, statement, if statement, right? So if statement eventually may compile to instructions like this. So we have JE, as you can see, E means equal. So if the status in that status register is equal, then we will jump to this label. Otherwise, it's like we don't have this instruction. So this one will look at the E flag. Then this one was not equal, this one is 0, this is greater, this one is greater or equal. This one is obviously less, this one is this is greater, this is less or equal. Okay. So for example, what we can do is we can have a compare instruction, compare EBX, EAX. So what we're doing is we are subtract EAX from EBX, but we do not store the value back into EBX. We're only updating we only update the flag registers. After flag registers, we have a jump instruction. It's a conditional jump. If it's a less than or equal to, then we will jump to down. Otherwise, we will just ignore this instruction, go to the next instruction. So those are control flow instructions. So here is compare. You can compare things, compare registers. You can compare register with value in memory. You can compare register with constant. Those are the things you can compare to. The next very important control flow instruction is the core instruction. So actually all of this we will go even deeper next class for the basic stuff. You have to understand that. But today I just want to give you a little bit a brief overview. So the core instruction is in a like in a say function call. In a say function call, you call function that it will eventually compile into a core function. So the core function will do several things. Okay, it will first pushes the current code location onto the hardware supported stack. Um, if you don't understand this right now, don't worry. Next class I will have more animations to clearly show you what's going on. So the current code location is actually the next instruction to be executed. We push that onto the system supported stack, hardware supported stack. So what it register specify where the stack, that's the ESP register. So we will push the return address to ESP, okay? When we say push, we means we first will decrement 4 to ESP, then push the value, store the value onto the stack. Then we will perform an unconditional jump to the code location of the label. So why do we push that onto the stack? Because after the function, eventually we have to come back. At the same level, you call a function. If after the function finishes, what do? You execute whatever is after that function, right? So whatever after the function, at the memory level, there's a location. That's a return location. So we need to push that return location onto the stack. Then later, when that function returns, we know where to return to. So now you can see that we are pushing some control location, which is a return location. That's not really a data. That's that's a that's an address of code, and that's the problem. A lot of security issues we will talk about next week. So for cores, you can call a label, you can call a register, you can call a memory location. So when you call a label, so that label is eventually compiled into something fixed. But if you call a register, the register value can be changed at runtime. So it's not really fixed. So if you call a label, this is called a direct call. No matter what architecture you're using, this is called a direct call. If you are call a register, this is called an indirect call. So in indirect call, you don't really know where you are calling to at a when you are not running the program. When you do a direct call, you know where you are calling to, even if you are not running the program. Then the next instruction is the return instruction. So this is the last instruction in each say function. If the function returns, it has this return instruction. So the return instruction, it doesn't take any parameters, any arguments. I think some of them could take some arguments to balance the stack, but usually you don't see that. Depends on the calling conventions, I think. So here, the return instruction is the opposite of calling instruction. So what it does is it pops an address off the stack. And that address is supposed to be stored there by the call instruction. But the return instruction doesn't really care if is the call stored that there. It will pop 4 bytes for 32-bit architecture. It will pop 4 bytes there from the stack. Then pop that 4 bytes into the program counter, which is EIP. So which means if you can overwrite that stored address in the stack, then you can make the program return to a different place from what it is supposed to return to. So that's the main problem of buffer overflow, which we will explore next week. Okay, so the runtime stack is for supporting of procedure calls and also passing of parameters between procedures. So procedures here, basically you can say functions. the stack is located in memory. It's part of memory. It's not part of the CPU, and it goes from high address to low address. By the way, I want to check. So when is our class supposed to be over? 7:50, right? Our class is 7:50, right? Or 8:50?
8:10.
8:10. So we still have like 1 hour, right? Right now it's 7 because right now I'm not at Buffalo, so I'm in a different time zone. So I'm trying to figure out. We still have 1 hour and 10 minutes.
Yes,
right?
correct.
Okay.
Yep.
Okay. Cool. Okay. So if we push a value, the ESP. If we pop a value, ESP will increase. There are some other stack operations. We already say push, we already say pop, and there are others you will say. For example, there is an enter instruction. So the enter instruction will call a function frame. The concept we will explore next week. So basically, the enter instruction is equivalent to those three instructions. It's equivalent to push EBP, then move ESP to EBP, then subtract a value from ESP. So obviously that immediate number also needs to be encoded into the enter instruction. So why do we need this? So here, since this is equivalent to this, why do we need this? It's mainly because we use those three instructions a lot for all the C functions. So most of the C functions, if we use the same calling convention, we always use those three instructions. Push EBP, move ESP to EBP, then subtract a value from ESP. So if we use those a lot, or for every instruction, then we can do some kind of optimization at the hardware layer. We introduce a new instruction that is equivalent to this. The benefit is it could be a little bit faster. We're only executing one instruction. We're not executing three instructions. Also, it will make our binary smaller. So each function used to have three instructions. Those three instructions could be, it's hard to tell how big those instructions are because Intel architecture, those instructions are variable lengths. For ARM, the instructions are the same length, but Intel, it could be different. So for example, there could be 4 to 7 bytes. So those three instructions could be 12 to 15 bytes, I'm guessing here. But if we just use one instruction, it could be very small. It could be 2 bytes or 3 bytes. So we'll make our, if this is used by every function, this can make our binary much smaller. So, but when you say this instruction in the disassembly, you need to know, we are talking about those three instructions. Then let's take a look at those three instructions. The first one is push EBP. So EBP is called the base pointer of the stack. Push something onto stack means we are saving it. So we are saving the previous function's base pointer or function frame to the current stack. Then we move where the current stack is to EBP. So we are setting up the function frame for the current function. Then we subtract some value to ESP. The reason we do this is probably we want to reserve some space for local variables. So in C, local variables are on the stack. Global variables are not on stack. Of course, there are other variables you can put on heap, right? But local variables, they are for each functions, and so those are on each function stack. Reserve some space there. Then later you can address those variables using EBP. So if we have enter, then we must have leave. So leave is the opposite of enter. It's equivalent to those two instructions. We move EBP to ESP. So the value of ESP is lost. We don't care the value anymore. The ESP now is the same as EBP. Then we pop EBP. Means we're popping what ESP points to into the EBP. So the value of EBP from the first instruction is lost, and the new value of EBP is restored from the stack. Okay, this probably is a little bit confusing right now, but we will talk about this next week. then you will be able to understand. This is very important for our buffer overflow experiments. Okay, so I actually talked about the ARM64 architecture, so we probably can skip this one. Let me see if there's anything. I think we can skip this one. Okay. Here I have another program. So this is just the one main function. As you can see, the function has a main C file that has a main function. The main function has a long a. Long means this one is a 64 bytes. Those two values are 64 bytes, and we want to add them together. So this is very similar to the previous program add. The difference is this one is we are adding two 64 bytes values. So let's say we want to compile this into a 32 bits program. And we want to also want to compile this into a 64 bits program. And then let's see how they are different. As you can imagine, for a 32 bits program, the registers are only 32 bits. So the register is not big enough to store the 34 bits value A, right? So this one, of course, this one is on stack, but eventually do some calculation, we probably need to put them on register. So we probably need to use two registers for this value. One register for the 64-bit version, one register should be enough. Let's take a look. Where am I? Okay, let's do two screens here. What we have? Air add. Okay, let's air add here. Okay, so let's do a clean here. Let's do a make. So now we have the 32-bit version of the program. Oops, okay, as you can see, this is a 32-bit version of this program. 32-bit. On the right-hand side, let's do the same thing. Probably. What is the? I don't remember what is the one I'm using. Okay, so we'll make air and 64 to generate the 64 bits here. Okay, but this part, there's a warning, doesn't matter. We'll generate this. Okay, so now we have two programs, and on the right-hand side, you can see this program is an L file, which is 64 bits. Left-hand side is the L file, 32 bits. Then let's use object dump 64 is a symbol of this program. How do I go up here? We are at, which one we're looking for? We're looking for main function, right? Oh yeah, so this is no, we're looking for the add function. Do we have an add function? Oh yeah, we have the air add function. As you can see, we have air add function. So just ignore the first instruction. This instruction here, what do we have? We have a move from memory location EDI to RAX. So as you can see, this is one using RAX, so this probably is 64 bits. Then here, this one doesn't matter. Then we move. Well, actually here. Then we are adding RSI to RAX. That's it. Basically, two instructions. We finish the addition. Those two instructions. And those registers are 64 bits. And you can see the addition here. That's the addition. So those two values are already stored. One of them is stored obviously in memory. Another one is already stored in SI. So we just add them together. Then let's go back to the 32 version. We use object dump. We use -d to disassemble this one. Then we put the name of the program here. Then it will give us the disassembly. Then we find the add instruction here. So here we have the air add instruction. So here we are using 32 bits. What we're doing is we first move some data from stack to EAX. We are only moving 32 bits, right? Then we are moving another data from somewhere memory EAX to EDX. We're moving another 32 bits. Then we're moving EAX, using the EAX as memory, then move the value to EAX. So anyway, this is still 32 bits. Then we add this one to this one. So here you can see we have two additions. Here we only have one addition. So this addition is adding two 64 bits value. And this addition, two additions. One is addition with carry, same as carry. We are adding two 32 bits. We added the lower 32 bits first, then we get a carry, then we add the higher 32 bits, then we get also we use the carry. So you can, this is how the 32-bit version of the same program different from the 64-bit version of the program. If you don't understand exactly what's going on, it doesn't really matter that much. We have two additions here for 32 bits and only one addition for 64 bits. And we're using different registers. This one we're using 32 bits register, EAX, EDX. Here we're using 64 bits registers like RAX or whatever, right? Okay. So I actually put the results here. So after the class, you can also try this. I also gave you the command here. You can just type that. Okay, next we talk about, we still have 1 hour. We probably don't have much time for in-class practice today, but we can finish the background. Next, we want to talk about the Linux file permissions. Obviously, each file, each directory has the three user-based permission groups. The first one is called a user. So a user is the owner of the file. So usually whoever created the file becomes the owner. The owner permissions only applies to the owner of the file or directory. The permission has at least talking about the read, write, execution. The group permissions can count a group users. So all users belonging to one group will have the same access permission to the file. The group permissions apply only to the group that has been assigned to the file or directory. Then there are others, which are not user owners or the group. And the permissions types, there are three basic permission types. First one is read, which means the user has a user. The user could be the owner, it could be other user, it could be a user in a group. He has the ability to read the content of file, or it has a write permission or execute permission, which means it can use this file as a binary and run that file. Or if this is a directory, it means it can view the content of the directory. For example, if you do a ls-l or al, you get something like this. So this is my old computer actually. So you can see I have many files here. Some of them are folders. For example, the blue ones are actually folders. I'm not sure why the JPEG are purple here. Doesn't really matter. So others are white ones. They are also files. Blue ones because they are directories. If you say the first one says it's D, means it's a directory. And it could also be C, or it could be also be B. Usually they are for devices. Those are under the device or etc folder. So C means it's a character device, like your keyboard, like your mouse, that's a character device. B means it's a block device. For example, your flash, your hard disk, those are block device. For those ones, they're not really device, so they don't have that. The D Then we have the permissions for owners, groups, and others. As you can see, the first three, they are permissions for owners. After that are permissions for groups. After that are for permissions for everyone else. So for example, this JPEG file, obviously it's not an executable. So I'm the owner of this file. So I can read and write to the file. And also any group can also, my group can also read and write to the file, but I'm the only one in this group anyway. Then everyone else on this system can read the file. They cannot write to the file. Okay. Then this one says how many link counts are there. This one shows who is the owner. This column shows who owns the group. This one is the file size. This one is the last time you modify this, and obviously this is the file. So those are the permissions for Linux files. The reason I bring this up is we need to talk about a very important type of programs in Linux systems. It's called the Setuid programs. So Windows doesn't really have the same mechanism. Windows doesn't have this. But this is a very powerful mechanism in Linux, and it's widely used the mechanism for all kinds of services, like you develop a web server, engine, something like that. Usually they are Setuid programs. So this is related to the loading stage of turning a C program into a process. And let's take a look. What is a Setuid program? This is a lot of information here. So if this is the first time you heard of a Setuid program, this is a lot of information. And besides Setuid programs, you can also set a group ID in Linux. So you know, each process, they have their own process ID. So that's like an identifier for a process. For example, that's usually called PID. And you can also have PPID, which means the parent PID. Who create for a process, who is the parent process, who created the process, then we want to know that process's ID. That's a unique identifier for each process in the system. However, a process may also have many other IDs, and they are related to security. Especially there are three UIDs. There are also those GIDs, but for this class, let's focus on the UID to make sense a little bit simpler. So the UIDs are used to specify who created this process and other purposes. Okay. For example, each process has widget. The first one is called a real UID or RUID. So the real UID is the UID of the user that created this process. It has nothing to do with this process. For example, we have a program like ls. When you are the user, you run the program ls. Then the real UID of the program is your account, is your UID. It has nothing to do with who owner of this UID is. Okay. Then we have effective UID. So the effective UID usually is the same as the UID, but it can be different. There are special programs called Setuid programs. Those programs, their effective IDs are not the real UIDs. They are the owner's UID. And the operating system, the loader, they use the effective UID or EUID to evaluate the privileges of the process to perform some kind of actions. They use the EUID. Also, there's the third ID called the safety UID. So if it's a binary file, and that binary file is a setuid file, the UID will be the UID of the owner of the file. Otherwise, it will be the real ID. Let's say a more concrete example. So setuid programs, first of all, remember the kernel makes decisions whether a process has a privilege to do something by looking at the EUID of the process, not the real ID, not the saved ID. So for regular programs, the effective UID is the same as the real UID, which means is the ID of the guy who launched the program. But for setuid programs, the owner of the program is not the guy who launched the program. So what happens is, if this binary is set as a setuid program, the process changes its effective ID from the default UID to the owner of the UID. So in most cases, we are using this for, here I have example. So we have the bin folder. The bin folder has many tools you use every day, right? So you can see we have bash, we have zip, unzip, or whatever, we have cat, we have change mode. So who are the owners of those programs? So each of them, when you do this on share, you call it command, but actually they're just other programs. So who are the owners of the programs? Who are the owners of the programs? Anyone here? Anyone here can answer me? Who are the owners of the programs?
It looks like root ownership to me. Still.
Yes. So those programs are owned by the root. So I'm logging as Zemin here, right? I'm the user own these programs. But can I run those programs? I can. I'm not in this. I'm not a root. I'm not in the root group. However, I'm other users. So as you can see, other users has an X here, which means other users can run this. Means I can run them. So when I run them, let's say if I run cat, this is not a setuid program. So when I run cat, the process of this cat program has a real UID of Zemin because I'm running this. And its effective UID is also Zemin because I'm running this, and this is not a setuid program. So this program doesn't need setuid privilege, but there are other programs that need setuid privilege. For example, you can see here, we have SU, which is switch user. We have unmount, is to unmount some device from the file system. By the name, you can see that those are sensitive programs, right? They are security related. We still want those programs to be run by anyone. For example, I'm Zemin. I want to switch to another user account, Superman. I should be able to run the program to do that. I don't have to be logging as root to do that. But obviously, by running that program, we need some root privilege to do that. Not everyone can switch account freely. That's why those programs, you can, if you use the GUI system, you can see they are actually, the background color is red. Those are setuid programs. The difference is here, you can go back to the user permissions of those programs. You can, the last one is not X. If the last one is X, it's just a regular program. The last one is S, which means the setuid program. So when I run the setuid program SU here, I'm Zemin. The program is owned by root. When I run this program, the real UID of this program is Zemin, it's me. But the effective UID of this program is the owner of the program, which is root, which means this program will be able to do what the root account can do, not only what my account can do. So this is very important for many system services and other operations. So Windows doesn't really have this mechanism. So Windows try to bypass this by setting up a service, something like that. They have a different mechanism for this. Okay. So this one, the S bit here. Okay. So let's look at another C program here. This program I call it read secret. Let's say what this program does. We have a file pointer. Beginning, it doesn't point to anywhere. Then we have a buffer, which is a local variable with 100 bytes. Then this program will get the UID, will get its own UID. Then try to get the structure password. So this one is not real password. What is this? So we get this UID's username. So UID's username. So first, this is we get UID. This is a system call. Eventually, this is a system call. Then we get the UID. Which we can have the UID and the username of this UID. Then we get the effective UID of this program as well. We get the effective username as well. Then we try to open the file secret. There is a file called secret somewhere. We try to open it. If we cannot open it, we say we cannot open it. If we can open it, we read it and we return. I guess we don't have time for the demo, so I will just show you the screenshot here. But you guys can do this. I can do this. What we are doing here is, let me see. Okay. We looks like my internet connection is not stable. Let's wait a little. Can you guys hear me?
Yep.
Okay, cool.
Yes.
Okay, so as you can see here, I log in as user. I compile this program, read the secret. So I'm the owner of the program. Then I switch to another account. I call it Superman. And I input the password Superman. Then in Superman, first I put some secrets in the secret file. Then we change the mode of secret file. So there was no, so basically I created a secret file. So the owner of the secret file is Superman. And I changed the mode of the secret file to 600, which means only the owner can read and write to this secret file. So after this, what we have is in this folder, we have this secret file, which is owned by Superman. And the access for it is only owner can read write. So I'm still, I try to catch this file, then I can get the result. I try to run the read the secret. I can also get the result. So when I run this read the secret program, the owner of the secret program is Zemin, but I'm running as Superman. So the effective, so right now this program is not a setuid program, as you can see here. It's X, it's not setuid program. So when I run this program has a UID of Superman and also the EUID of Superman. It has nothing to do with the owner of this file. Okay, so the user of Superman, the EUID Superman has a permission to read the file. That's why we can output the file. I didn't, the screenshot was cut a little bit, but you can see we can output the. But if we change this file a little bit, let's say, okay, I changed the file a little bit. This program is changed. This program's owner is changed to Superman. And other people can run this program. Then I log in as Zemin. So now I log in as Zemin, I run this program, the program try to read the secret file. So the UID is Zimming. The EUID of this process is also Zimming. However, the EUID is to the file secret, right? That's why the program will display cannot read the secret because I don't have the permission to do so, right? Also, I can do the same thing. I can just do a cat to the secret, also permission denied because I don't have the permission to do that. Next, we can change the program. So next, we log in as the Superman again. We change the program's permission to not 0.5, but a 4755. 4 here, the 4 is important. The 4 changes the program to a set. So now you can see here, read secret is still a program that owned by Superman, but it's a set UID program. And anyone can run this program. Okay, so now I log in as Zimming. As you can see here, I exit as Superman, I log in as Zimming. Now I run this program. I run this program. Now when I run this program, this process UID, because Zimming is the one who launched the program, but the EUID is Superman, because the program itself is a set UID. So the loader will change the EUID to the owner of the program. And the owner of the program will be used to evaluate if they have the permission to read the file. And as Superman has the permission to read the file, and I can print out the content of the file. So this is how a set UID program works. So we will use this mechanism. So for some of the challenges you are doing, we will use this mechanism to save the secret. So basically, you need to hack into, you need to hack a set UID program which have access to the next level's user's password, and you will be able to get it out using a software vulnerability somewhere. So that's why I introduced you with the Setuid program. And there are some readings you can do about Setuid programs. Also, there are papers about how it works. That will be the homework part. The next part is the L files. We're almost there. So L files, the full name is executable and linkable format. It's a very common format for all kinds of executable files, object files, and also shared libraries, and also core dumps, because when you dump something, you dump the code as well. And there are several possible file extensions for L files. Obviously, for Linux Unix systems, the file extensions don't really matter that much compared to Windows systems. But you probably have seen those extensions. The most common one is there's no extension. When you compile something, for example, the make file I showed you just now, several programs were compiled. We never used any extension there. You can also use elf extension, .bin extension, or .o for object files. For KO, it could be kernel modules, and also SO usually for libraries. So elf files obviously has the programs, which means the code, and also has data. It also has meta information about how a program should be loaded. So the loader will use information to load the program. It also has metadata describing the program components, what headers are there. We can use a command file to say if a file is an elf file. We just use it multiple times. For example, we do file on the bin ls. We can say this is my new laptop actually. You can say here, we can say this is a 64-bit elf file, and it's dynamically linked. It uses this interpreter. Its hash value is this. It's stripped, which means the removed. So to make the file a little bit smaller, make it a little bit harder to debug. If we use other tools like readelf. There's a tool called readelf. Use readelf, you can get all the information of the elf file. For example, you can get the headers. So elf headers always start with 7F 45 That's basically elf, right? That's the ASCII of elf. 7F is E. I think so. Huh. That, okay, I'm not. Okay, 7F is not okay. 45 is E. 4C is L. 46 is F. That's correct. So 7F is just a fixed number. So it always starts with those 4 bytes. So that's called the magic number, magic code to show this is an elf file. And use readelf, you can get all other information. For example, this is a dynamic linked object. Where is the entry point of this program? And what are the section headers? Some of them we will use later for hacking. There are 2 important ones. One is called interpret, another one is called load. So interpret part basically defines should be used to load this elf into memory, and node define parts of the file that should be loaded into memory. And there are many sections, and usually they are in load. For example, .text section, that's where the binary code is. The binary code is in text section. Then there are PRT, as you can see, PRT, and there are GOT, global offset table. So those are used to resolve and dispatch other binary. Dynamic link, you want to call a function that is not part of your binary because they are dynamically loaded into memory by other programs, by the loader, and it's not part of your binary. And that library could be shared by multiple programs. In these cases, they may have different virtual address at different process address. Then the loader needs to resolve those addresses, and they put those into these locations. So at the file, they will reserve those places. At the runtime, this will be updated. Also, data sections usually used for global data, like global variables in C. And those usually are initialized data. For uninitialized global data, usually they go to BSS section, which is the uninitialized global data section. But compare those two, you can think the loader will treat them differently. If a data is initialized, global data, it means that the value for initialization has to be stored somewhere in the binary, right? And the loader will put that data, when the loader set up your program, the loader has to set it up before your program can run with those initialized values. But for BSS, since they are not initialized, so for those initialized data, we literally have to load this data from binary. But for BSS, uninitialized data, they will have address in memory, but the value of them doesn't matter because they are uninitialized. So the loader doesn't have to copy anything from the binary to the memory because there's no initialized value. They probably even doesn't need to, they have to memory reset that. For C standard or uninitialized, that has to be 0. So it has to reset that to 0, but they don't have to load anything. There are also read-only data. For example, there could be a string. The string is never modified, and we can put that in read-only data. And read-only data, when they are loaded to in memory, we can set those memory page permissions to read-only. No one can read that. No one can write to that. If you write to that, it triggers some kind of segment fault. Yeah. So there are many tools for ELF files. First, we have a compiler, GCC. We have readelf to pass the headers. We have object dump, I just showed you. It can pass the headers. It can also the code. We have nm to show you the symbols. We can use patch elf to change some of the header properties. We can also use object copy to swap out some sections. We can use a strip to remove other useful informations. And also there are libraries for you to programmably change those things. We probably will use those tools. Depends on. So you can today after the class you can take a look. You can try those tools to see what they're doing. And when you approach a hacking problem, you need to quickly figure out which tool you need to use, which tool will be the most convenient one for you to use. Some of them can do the job. Many of them can do the job, but some of them is just easier to use. Okay, after talking about the static structure of a Linux binary, we talk about the memory map of a Linux process. So obviously a process is loaded by the loader from the binary to the memory, and when it to the memory, it has a slightly different structure as their counterpart in the hard disk. First of all, we talk about 32-bit version. So each process in the OS run on its own memory sandbox, and that sandbox is called the virtual address space. In a 32-bit machine, it has 32-bit linear address. The size of it is 4 GB. Okay, so those virtual addresses, they are mapped to physical memories by page tables maintained by the OS kernel, and not only, and also it's related to hardware. The hardware, the CPU has some registers to specify where to look up and how to translate them. Some of the translation is actually done by, for example, by MMU, which is hardware. It's not a software. So, of course, some of the devices doesn't have MMU, which is a different case. Then here we can see a memory map of a 32-bit program. So you can see first we have the text segment on a very low address, and those are just the code. This is like a very legacy design. Used to be like this. Right now, everything can be randomized. The reason we randomize them is for security. So first we have the code section. This is like the .txt section in the binary loaded into memory. Then we have the data segment, usually the .data segment. After that, we have the BSS segment. Then we have the heap, which doesn't really map anything to the binary. It's dynamic. On top of that, we have some memory mapping segment. Usually for mapping, we can use mmap system core to load other load other libraries into the memory address of this program. So the even higher address, we have the stack. The stack is, so as you can see here, we are only showing one stack, but actually each thread has to have its own stack. So we can divide this into multiple stacks, but each of them will go to lower address. Each thread is an instruction, it's an execution unit. It has to have its own stack. Otherwise, they will interfere with each other. On top of that, we usually map some kernel space. So this is what the memory map of a 32-bit system look like. So all of you know we have a non-pointer in C++, which means just 0, right? The possible definition of it is for older version, it's just defined as 0. For newer version C++, there is a keyword for it. So, so if you access this, what will happen? It will trigger a segment fault, right? If you access this, if you run code from here, it will trigger a segment fault. But how is that actually implemented? Do you ever think about that? Because think about it, this is just memory address 0. It's nothing special than any other memory address. How is this different from memory address, let's say 80,000, blah, blah, blah? It's not that different. Why we access 80,000, it will not trigger segment fault, but we will access this, it will trigger segment fault. Why is it? Anyone think about that before? Any idea?
Because it's in kernel space?
It's not accurate, but you are getting to the right direction. So
I think it's something related to virtual memory.
Relating to what?
Virtual memory.
Okay. So both of them are touching the right direction. So basically, at a C standard or C++ standard, we want it to be, illegal to reference or dereference address like that. That's what we want. We want the developers, whenever they do that, we will give them an error. But how is that actually implemented at the OS layer is, we will just map the first memory page as invalid. So the very first memory page is always wasted. So it's not like you just do 0. Even if you do 1 or 1,000, you will get the same result. You will get a segment fault because they are in the same memory page. That memory page, that's a virtual memory page that doesn't map to any page, and that virtual memory page is set as invalid. It should never be used. Okay, so that's how we implement that. We actually use the same trick a lot. For example, let's say, it's not showing here. For example, the heap will go up, the memory mapping will go down. It's possible that they will touch each other, overlap each other. That will trigger a problem. So at the OS level, what we do usually, we will set a page is invalid. So if the heap touch there, then we know it's using too much space. Then we generate an error. Or if the memory map going downward, we trigger the same thing. So they will never overlap each other. So this is a trick we usually use at the OS level. Then if you want to say I forgot to give you this program. I will add this later. So here, let's do an example. I think we still have time, right? We probably have 30 minutes something. Okay. Just use one here. Okay, where are we? Let's go to program map. So what do we have here? I have a simple C program which does nothing. The purpose of this program is just to show you memory map. So this program will just try to get a char, get a character from the keyboard. So basically it's blocking itself there. Okay. So let's see if we already compiled this program. Yeah, so PM here, we have this program. So which command should we use? Oh yeah, we'll just get a PM running here. Yeah, we should use this. Okay, let's first run this program PM. Program is running and it's blocking there. I'm not giving it anything. You can see. Let's get the PID. Oh, that's too much. Let's just do this. Okay. Let's get the PID of the program, which is 27x. Then what we can do is we can cat. Let's just another command. Pmap. Pmap x. Then we put the PID 2748113 there. Okay. So now we can see, so this command give us the map of this program from low address to high address here. As you can see, what do we have here? We have the permission of each module. Some of the module is executable, some one is read only, some one is read write, and we have a name for them for that part. For example, here is a heap. Before the heap, we have what? We have those binaries or datas, which are from PM. So you can see some of them must be code. For example, this one is from PM. This one, actually the second one, this one is from PM, and it is X, executable, which means it must be code. And some of them is read only, so probably read only data. And this one is read and write, so probably this is BSS or data section, right? Then after that, we have the heap. Then after that, we have what? We have libraries. Those are the C libraries, as you can see. Those are C libraries. So C libraries are mapped into this function's memory address. That's how this program can call C library functions. Of course, there are those are not important for now. Then you can see that upper address, we have the stack and a very high address. So this one is 32 bits, let's say 32 bits. So this is actually almost at the top of the memory. We have the stack. So the stack goes down, the heap goes up, and we have a library goes down. Then we have other libraries and also the PM here. You can run this program. You can do the 64 bits of it and also 32 bits of compare to say how they are different. I give you the command here, so you can try that. This one, it's actually the same thing, so I will skip this one. So the 64-bit, you can say it's a little bit different. We have those modules, heap, stack. We have other sections or for fast system call or whatever kernel operations. Okay, the next one we talk about system calls. Most of you didn't take a operating system class, so you probably don't know what system call is. So basically, system call is the interface for a process or an application to talk with the kernel. That's the interface. So anyone know what is the interface for kernel to talk with the application? The other way around. Does anyone know that? System call is the interface for program to talk with the kernel. What is the interface for kernel to talk with the program? For Linux or Unix system? Any guess? No? Okay. Usually it's signals. Do you guys ever use signals? So signals is how, signals is how the kernel or other programs talk with other programs in the system, and the system call how an application talk with the kernel. So the kernel provides some kind of service using system calls, and the program can invoke system calls, and the system call will make the CPU onto the kernel, and the kernel will perform some service, then eventually return back to the program. So obviously the program alternates between executing in user space and the kernel space. Of course, usually even if you are programmed in C, you do not directly invoke system calls. You use some wrappers. You use some in the C library to do system calls. There are many system calls. For Linux systems, there are over 300. For Windows, people say there are over 700 system calls. And some of you may heard that DARPA had a cyber grant challenge several years ago. which is a machine versus machine CTF. Just a search cybergram. You can find it online. There may be even a documentary about that. So in that competition, 20 teams in the finals, they hack each other in a customized system. That system has only 4 or 5 system cores. It's not like a fully functional Linux or something. It's a customized kernel with several function cores. So they wanted to make things easy. So you already, as long as you program C, you use many of those functions. Okay. So many of those functions, they are C-level functions, and they are also system core level. They are also system cores. So for example, there is a C-level library function called open. That open function eventually maps to a system call called open. And also there is a read function. Eventually it calls the system call, which is also called a read. Also there are fork, exit, kill to send messages, right? So usually there is a mapping between a system call and a C library function, and sometimes they use the same name, but not always. For example, the change directory C function invokes the underlying change directory system call. There is a tool for us to trace the system call of a program. For example, here we have the tool is called S-trace. S stands for system call. Usually we can use this to quickly do a recon on a program. For example, this program we have here is PM. Let's do an S-trace on PM, right? So when we do an S-trace, what do we say? The first system call we have here is execute, okay? But actually before that, like I said, this is a shell. In your operating system class, you probably developed a shell before. So how do you develop a shell to start a new program? You need to fork your system called fork. Then eventually you use execute. But from here, we only record from execute. So here we can say the first one is execute. We execute this program. Then we have a break to get the current. This one is get to, I think the break is get a heap address or something. Yeah. This is called break without parameters. Then there are other, for example, access to say if we have this library. In this case, we didn't find the library, but it seems not matter. Have a memory map. So here we are getting a memory. We get some memory location at this address. This is anonymous memory location. So we just get some memory in this program's its own memory space. We don't know how we want to use it. Maybe the loader want to put something there. And then we have another access to try to find this file. It's not there. We also try to find other files, another memory map. Then we close 3, the file descript 3. Which one is 3? 3 is standard is 1. I'm not sure which one is 3. Okay. Anyway, then we are reading the beginning of this. Looks like its own file here. From 3. Then do all kinds of memory map. So this memory map looks like we are putting this program into the memory, looks like. Then we're doing change the permissions. Then we set up the heap, everything. Now, remember, we are using the function called getChar. So now we are inside the system called read. We blocked here. We're trying to get the char, right? So let's give it a char. Then the char eventually go back to that letter G eventually go back to the program. So the read system call, we're getting us the char G. Of course, there is also a return there. So that's why we have get 2 ones. Then after that, the program doesn't really do anything. That's why we just exit with 0. So use trace, you can get what system calls these programs are making. As you can see that even this program is so simple. Okay, this program, we're not doing anything. We're just getting a chart. But the program itself, it will do so many system calls. Only one of them is triggered by our program. Only the read here is triggered by our program. All others are triggered by the other parts by the compiler or the loader, whatever, right? So strace is the one we use to get the system. There is another one called trace. So trace can tell us what function calls, library calls this program is making. In this case, it looks like we don't have any. Okay, so even this one is not giving me the output. Okay, I'm not sure what's going on. But trace is supposed to give you some library calls. Strace is supposed to give you the system calls. So next, we need to take a look at how system call is actually made. So in this architecture, system call is actually made using a special instruction called int instruction. And for Linux, we use hex 80 as the int instructions argument. For Intel, I believe it's different. It's 20. Sorry, not Intel. For Windows, it's 21 or something. If someone, I think it's 21. Basically, it's just give the control to the 80s interrupt tables. There is a then we're trying to find the 80 hex the item and use that as the interrupt service. For Windows, you may use a different service. That's why it's 21, not 80. And this instruction will call the CPU to undo kernel, and the kernel will take over. So this is actually the argument we use when we use system calls. Remember, we're using, let me show you this. Okay. So this is what we are actually doing, the disassembly or assembly code for making a system call. When you say this int 80, you will know they are making system calls. So they are using those registers to pass parameters for system calls. Then you can search a table like this to see what are the register values. So the EAX is the system call number, and the name is not actually specified anywhere. The machine code doesn't care about the ASCII names, obviously. So those are numbers. For example, if you are doing a system call open, the EAX number will be 5. So let's go here. This is a system call. Let's see what is the EAX number here. Let's do it quick. Okay, here we're doing move B to EAX, AL, right? So what is the value of EAX here? It's B, right? Because we're moving B to AL. AL is part of EAX, which means the system call number here is B. B is what? B is 11, right? So we're talking about this one. So this is the execute system call. Then you can say what is supposed to be the parameter for that. This one is not compatible with the one I'm using, I think. For example, so here we have those strings. This is actually a string. That string is basically, so first one we do EAX, we XOR, so we get a 0 for EAX. Then we push EAX to the stack. Then we push the string to the stack. Then we will move ESP to EBP. So ESP basically to here. Now we move EBP there, means EBP pointed to the string. So this string is actually a bin slash L. It's a bin or something, or bin slash, anyway, it's a shell. Then we do execute. Then basically this system call will create a new shell for us. And okay, you can see this can be used as a shell code. So if we get this, oh, it's actually this one. Yeah. So you can say this is the system call parameters. First of all, what? We need a string. a string should be ended as with a 0 here. So it's a bin sh. Then we have the environment variable, which is 0. We have another argument, and this is in ECX. So this is a string of this, the address of the string. So if you carefully check this program, you will see it's actually setting up the EAX, EBX, EDX to the correct value. After setting up this, they will do int 80. Then we go to the kernel to get the new process. We only have 5 minutes left, so we need to be a little bit quicker. Let's skip this one. Okay, environmental variables. Maybe we can skip this one and talk about this next week, because we're not going to use this until I think. One thing you need to remember is the environmental variable actually is stored on the stack, and it's on the top of the stack, along with the command line arguments. So the loaders will put it there for the program. So as long as it's put on the stack, the program itself, it can look at the stack to figure out, oh, what are the environment variables I have? What are the command line arguments I have? It works. Okay, then reverse engineer tools. Today I showed you object dump. I don't think I have time to show you Ghidra, but I installed that in the virtual machine, so you can just play with it. I also put some GDB commands there. You don't need to remember those at this moment. When we will be there, I will teach you how to do this. Okay, we don't have time for this. The homework is due before next class. You need to submit through, for graduate students, you need to submit through the, let me open it up. Let me give you a quick overview of the, where's my system course homework? Okay. Let me give you a quick overview of how homework works. There are some readings every week. You need to read all of them and mark it here. Just to give it a little cross here to show you already read it. You may need to spend some time on this. Then there are several hands-on tasks for you to do. For this week, the tasks are, the last one could be a little bit challenging because we didn't really have time to do reverse engineering. But if you have any questions, just ping me on the Slack channel and also discuss with people. Task 1 is read the syllabus. In the syllabus, I actually embedded some secrets there. You need to find out. You need to find out the secret in this format. You just need to find it out. Then you need to list all the Setuid programs under bin and explain the commands you used. Take a screenshot, explain a little bit. Use the asterisk on a program you choose. Take screenshots. Explain some of, try to understand those system calls. Like I said, just Google. Just Google, find out what are those system calls, what they're doing. Okay, you need to give me at least 3 or 4 system calls from the output, explain what's going on. Also use error trace on a program you choose and explain to me the results. Also, you need to compile a C program. You can use the one I provided in the class into 62 bits and 60-bit ELF. Then use pmap. I gave you the command in the slides to show the memory map. Take a screenshot, explain what is what. To explain what is what, you may need to do some search by yourself, or I may have give you some reading materials there. The last task, depending on your skills, it could be very challenging, or for some of you, it could be simple, very, very simple. I gave you a program. The program name is Crack Me. So I already put it online under homework. So in the homework folder, you can say there is a Crack Me program and also the Word document. The Crack Me, you can put this Crack Me folder in a program, run that on any Linux box or the virtual machine I gave you. This program has some secrets. and you are supposed to reverse engineer it and find out the secrets. That's what you are supposed to do. You can use all kinds of tools you want to use. You can use GDB to debug it. You can use object dump. I don't want you to use Ghidra, but if you have to, I don't mind. But I don't think it will make your life that easier, even if you use Ghidra. You still need to learn what's going on. So, okay. I cannot tell you too much. What I can tell you is the secret is a string. And as long as you find that string, it's very obvious it's a secret. Okay. You need to crack this program to find the string. A lot of challenges in this class will be like this. I will embed some secret in the program. You are supposed to find it sometime, but I put a gate in front of that, obviously. So this one, it's a quite, there is not much, as long as you can do reverse engineering, you can do it. For others, it's like you have to go through some buffer overflow or go through some integer overflow to get the string, but that's the basic format. Okay, so any questions? Say something, say something. I'm not sure if you guys are listening, to be honest.
We are.
Okay,
Yeah,
good.
I don't have questions.
No questions. Yeah.
Okay, okay. So if everyone is good, I think that's it for today. Today is just background. Next week could be quite challenging. That will be our first session on buffer overflow. I will try to make it very straightforward, but still it could be quite challenging. After that, each level will be even more challenging after that. Yeah, good. Okay, so I guess this week. See you guys next week. Don't forget to submit your homework, okay? Okay,
See you.
bye. See you.
Thank you.
Bye.
Thank you,
Thank
Professor.
you.
Bye-bye.
Yeah.
See you next week.